All right. Good morning, everybody. I hope everybody had a wonderful weekend. And welcome to the last unit of material. We're actually going into the final phase of this course where we go in through chapters 8 and 10, which is going to actually be very nice. It's a nice way to end out the course because it's a lot of the materials, usually for most students, a lot easier. I want to start this morning by just announcing that this week is Mathematics Awareness Week at CRC. And so if you go to this website, you'll see there's just a lot of games and prizes and fun stuff like that that we have going on throughout the entire week. It culminates in the integration bee. And so you'll see there's talks going on both by individuals that are within industry and by students who have pursued mathematics after CRC or even at CRC. So I recommend if you love math, take a look at the CRC Mathematics Awareness Week website, and you might find some like-minded individuals to listen to there. It's really our annual big event, although right now, just because of COVID and everything, it's been slightly on hiatus for the past 2 years, but still such a fun event for most students. Let me get my screen going here. Share screen. And there we go. Pop this around. So, where the heck are we? We're starting into section 8.2 this morning. Let me get chat box open. There we go. We're starting in section 8. Sorry, I said 8.2. I meant 8.1. It's been that type of morning. We're starting in chapter 8. How's that? We're starting in chapter 8 this morning. And chapter 8 is really, in my opinion, just about one, it's actually about three things now that I think about it. It's about arc length, surface area, which is related to arc length, and then an application, a very specific application that becomes kind of important in physics and in Calc 3. So let's dive right into it. It's actually not bad. You're going to find, hopefully, you're going to find this material to be much easier than Chapter 11, which is why I choose to do it at the end of the course rather than in the order that it's presented in the textbook. You do not need this material for Chapter 11 at all. It's completely disjoint from Chapter 11. So it's very nice to then hop back to this to round out the course. So let's talk about this. Arc length. Given the function f of x equals sine of x, we now have a lot of skills. We can compute the area underneath the curve, right? So the integral from a to b of sine of x dx. Calculate the volume if we're rotating about a horizontal or a vertical line. And approximate the value of f using a Taylor series expansion, right? So sine of x is equal to the summation n equals, well, I should probably write that down. So our options are, maybe I should say, the area would be the integral from a to b sine of x. If it was a volume, let's say, rotated about the x-axis, for example, it would be the integral from a to b of pi sine squared of x dx. It's pi r squared. Right? If it was the sine curve rotated about, let's say, the y-axis, well, that's a little trickier. Remember, it's the circumference times, circumference, height, and width, and radius, actually. So 2 pi r, actually, I think it's circumference already has it in there. So it's 2 pi r, circumference, height, and width. And that'd be 2 pi r times the height times dx. And that would equal integral from a to b of 2 pi. The radius to the center axis of rotation would be x. We have sine of x dx. And by the way, in chapter 6, when we were learning this stuff in chapter 6, we could not evaluate this integral. And that's because we didn't have integration by parts yet. Now that we have integration by parts, we could totally do that. And then finally, we just recently found out that sine of x has an infinitely long polynomial expansion centered at 0. That is of the form summation n equals 0 to infinity, -1 to the nth, and then x to the 2n plus 1, because sine is odd, over 2n plus 1 factorial. So these are all the things that you can do so far with something like just something simple like the sine function. Very nice. First one is an area. Second one is a volume. Third one is also a volume, just about the y-axis. So anyhow, we've done all that. Now we turn our attention to the actual length of this curve. So what is the length if you were to draw this out and maybe over a real nice clean interval? So let me go ahead and grab my ruler here. And let's pretend as though we have some sine curve. And I'll use blue for the sine curve. So let's say that our sine curve looks something like this. And let's just pretend as though you just want the length of the curve from there to there. Okay, so it's from 0, let's just say, to actually let's pretend as though we went all the way to 3 pi over 2. Why not? So from 0 to 3 pi over 2, what is the length of that curve? We can motivate the idea of finding the length of the curve very easily just using the same ideas that we started with in the beginning of the course, which is kind of why they parked chapter 8 right after chapters 6 and 7, because you're really at the early parts of the course at that point. And so you're used to doing the mechanics we're about to do now. But you'll find that it's nice to review these mechanics as we get closer to the final exam. So the easiest way to motivate this is just to say, let me take an arbitrary slice. We're going to slice this interval from 0 to 3 pi over 2. We're going to slice it into n subintervals. I'll just say 1 slice into n subintervals. 2, we're going to look at the ith slice. Let me show that here. Let's say that the ith slice starts at x sub I minus 1. I'm making it somewhat large here just for ease. So here's our ith slice right there. And what we're trying to do is we're trying to find the length of the curve along that ith slice. So let me put in red here. Approximate this length. And then what we'll do is we'll add up all those approximate lengths. Now, if you're awake, which I'm kind of not right now, but you might be able to visualize how you could find the length of that slice or that arc length in that slice pretty easily. I'm going to explode the view a little bit. And I get that slice, so this is the arc of ith slice. I get that arc looks more like a line. And I did that on purpose because if you take any curve and you zoom in close enough, it'll look like a line. It won't look like a curve. And so it gives us a pretty decent way of doing this. I'm going to call this arc length. I'm going to call this a change in distance. Remember from your trigonometry and pre-calculus courses that S was always considered to be the length of an arc. I don't know if you remember that. What I'm about to write down does not pertain to this material, but I'm just going to write it right over here. S equals r theta. If you remember that formula, the S was the arc length in a circle of radius r when you cut out an angle of theta in radians. Now, we don't need that actual formula, but I'm just showcasing why we're choosing the letter S there. And we're saying delta S because it's just a change, a wiggle in arc length. It's a very small wiggle in arc length. And if you take a look at how we slice this up, the horizontal distance right here is actually just a wiggle in X, and the vertical distance right here is just a wiggle in Y. Let me go ahead and write that in our bigger picture. Now, again, I'm writing in this that it's a right triangle, but in reality, that red line there is slightly bowed. But it turns out there is a theorem from trigonometry that most of us don't even focus on too much. But the reality is that if you have a small enough slice, it's linear, or it can be approximated very well by a linear relationship. So we can consider that delta S to be a line if we want to. And now we can relate delta Y, delta X, and delta S, obviously, through the Pythagorean theorem. So this implies delta S squared is equal to delta X squared plus delta Y squared. I love this part of calculus because it really just goes back to our good old algebra and kind of the easy algebra, right? The good old Pythagorean theorem. Now, I'm going to go ahead and take the square root of both sides. Since an arc length is never negative, I'm not going to worry about the plus or minus on the square root. Arc lengths are just not negative. The other thing I'm going to do, the final thing, is I'm going to split this into two possibilities. And these two possibilities give us whether we're integrating with respect to X or integrating with respect to Y. Let me go and zoom out slightly, and I'm going to grab this. I'm going to create case 1 versus case 2. In case 1, we would factor out a delta X squared. If you factor out a delta X squared out of that square root, you would get a delta S is equal to the square root of the quantity 1 plus delta Y squared over delta X being squared. And then we factored a delta X squared off of both those terms. That's why it's a delta Y squared over a delta X squared. And by the way, you can take the square root of that delta X squared. So this ends up being the square root of 1 plus delta Y squared over delta X squared. And then we have a delta X hanging on the outside because we took its square root. And if delta X is approaching 0, delta X ends up becoming a dx, and delta Y becomes a dy. So you have dy over dx squared. And you get that formula. That tells us a very small wiggle in arc length. In other words, our little teeny little arc length there is just equal to the square root of 1 plus dy dx squared dx. Along the same lines, if you are integrating not with respect to X, but instead, if you're slicing the world with respect to Y's, you do the same thing. Factor out. Well, same idea. Factor out delta Y squared. If you had done it that way, you'd get delta S is equal to the square root of a delta X over delta Y squared plus 1 and a delta Y. Again, I factored out a delta Y squared out of both those terms. Delta Y squared divided by a delta Y squared is just a 1. That's where this 1 comes from. And the delta X squared divided by the delta Y squared is a delta X over a delta Y being squared. And then because I factored out a delta y squared, you take the square root and it becomes just a regular old delta y. This is the very same argument I use for the delta x move over on the other side. And again, the same idea. If I allow my wiggle in y to become infinitesimally small, then dx, or delta x, sorry, also becomes infinitesimally small, so it becomes a dx, and delta s also gets infinitesimally small, so it becomes a ds. So this will imply ds is equal to the square root of dx over dy squared plus 1 dy. Those are the two major formulas for the rest of the course. You will use them quite frequently. And the derivation of both of them is fairly logical. It's just drawing a picture, delta y, delta x, delta s, Pythagorean theorem, and then choose which one to factor out. Now, you won't recreate this proof all the time, but the idea of the proof is always there. You can always rederive it if you forget it. And the fact is that we have now approximated that red arc length, which I'll call ds now. And you have a ton of those little red arc lengths. Here's the next ds, and 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 so on and so forth down the line. So when you're finding the length of an arc, you're just adding up a bunch of these little wiggles in arc length. That's all you're doing when you're finding the length of an arc. And therefore, it should make sense that the length of the arc, at least in our case right there, from 0 to 3 pi over 2, would be the integral from x equals 0 to x equals 3 pi over 2 of ds. That is, remember, integral really means, it's a fancy notation for add up a bunch of stuff. We're adding up a bunch of arc lengths. And the ds that we choose will just depend. Are we integrating or slicing with respect to x, or are we slicing with respect to y? Everything from this point forward, every time that you integrate, you're just going to ask yourself with respect to y or x. If it's with respect to x, then you're going to replace ds with the square root of 1 plus dy dx squared dx. So in our case right here, I'm not going to integrate it. Actually, I could, but we would replace the ds here with the square root of 1 plus the derivative of our original function, which was the sine function, squared. So that's going to be cosine squared. And then dx. Now, this is the hard thing about arc lengths, is that most of the time with arc lengths, you end up with integrals involving radicals. And integrals involving radicals often are either challenging or pretty much impossible to do analytically. So you have to use something like Simpson's method or the trapezoid method or the midpoint method or something like that to get an approximation. So that's something that you'll have to do. And obviously just asking, why is it cosine squared? It's because it's the square root of 1 plus dy dx being squared dx, and y in this case was sine of x. So dy dx is cosine of x. And then we're going to square it. So anyhow, the fact that you're dealing with radicals all the time when you're dealing with arc lengths, it does lead to a lot of integrals that you have to do numerically. So just giving you a heads up, this is not my choice. This is just how it works. Arc lengths tend to be kind of gnarly like that. luckily, we start with the first few examples that don't involve that, and we'll end this section with an example that just showcases that mindset. But this is the basics. This is just it. This is the rest of the course. Every time that we're doing something, pretty much, I mean, there's an exception, two exceptions actually, where you're not using an arc length. But every other time that you're using arc length, you're using this formula over and over and over again. It's really a very nice formula to use, other than the fact that you end up with radicals. So let's go ahead and just take a look. I actually have the full theorem there. Arc length, if f prime is continuous, well, that is a requirement that your derivative be continuous because you're integrating that derivative actually. So if your derivative is continuous on the closed interval a to b, then the length of the curve on a to b is the integral from a to b ds. In other words, you're summing up all those little arcs. So you're summing. You're summing up all those little arc lengths from a to b. And by the way, I didn't tell you if it was x equals a or y equals a to x equals b or y equals b. It can go either way. And then say here where, now this looks different, where s of x is equal to the integral from a to x of the square root of 1 plus f prime of t squared dt. Now, I do want to mention this piece right here, that is just ds. That's 1 plus the derivative squared d whatever. They put dt. I put dt here because I didn't know if you're integrating with respect to x or y. So if you are integrating with respect to x, replace t with x. If you're integrating with respect to y, replace t with y. How well, actually, you wouldn't do that here. Now, let me retract that statement. This is the arc length function right here. But I just want to let you know, I wrote in here, but it's also the author will do it. This is not a very common move, but if you want to know the length of your arc from A to some arbitrary value, it's the length of arc, let's say of y equals f of x, from x equals a to x. That seems weird, right? So starting at some value a to some value that somebody later on is going to walk in and hand you. So this is slightly different than the main theorem, which I wrote kind of right here. This is the actual length from 0 to 3 pi over 2. Let me just point an arrow at that and make sure you know that that is the true length from 0 to 3 pi over 2. On the other hand, if somebody said, I don't know when I'm going to stop, I know that I'm going to start measuring the length of that curve at time 0, but I don't know when I'm going to stop measuring. So could you just find me an arc length function so that wherever I want to stop measuring, I can just plug in that value and it'll give me the true arc length? Yeah, sure, I could do that. That would be this. S of x, again, S stands for arc length, is equal to the integral from 0 to x. It's a function of x, and I'm plugging in the upper part x. Now, you should remember this, possibly, from your Calc 1 class. Most people don't remember this, so kind of understandable what I'm about to say that you don't remember it. But when you build an integral, if you have a variable within your limit, like in this case, we have an x in the limit, this stuff in here cannot have that x. It has to be a completely different variable. So that stuff in there, we're going to write, I know it's normally 1 plus the square root of 1 plus the derivative of our function, which was the cosine squared, right? And normally we'd say cosine of x being squared dx, but because the variables have to be different between the limit and here, we're going to go ahead and say it's cosine squared of t dt. Changing the letter does not change the integral at all, but just allows us to hand this to somebody and tell them, okay, you want to find the arc length or the length of the sine curve? Length of y equals sine of x from 0 to x. If you want to find the length of that curve from ending at, let's say, 27, all you need to do is plug in 27 here. Once you do that, you can integrate and find out the length of that curve. So this is more of what we call black box function, where somebody comes in, you're just like, okay, well, if you don't want me to tell you what the area is from 0 to 3 pi over 2, instead, I'll just give you the area from 0 to, or I'm sorry, the length. If you don't want the length from 0 to 3 pi over 2, I will just build a function that gives you the length from 0 to wherever you want it to stop. Of course, that means that you, who wanted to stop at some arbitrary number, are going to have to run the integral, because I don't want to integrate this by hand, because this is not a fun integral. This is one of those that I'd probably have to do numerics with. So anyhow, that's a heads up. That was mixed into the theorem, and so I thought I'd just go ahead. That's called the arc length function. Right there. So the theorem just says, if you want to measure the length of an arc, you're going to sum up all the little arcs from A to B. If you don't know when you're going to stop, and if somebody just wants an arc length function, well, you'll do it like this. And so, as we wrote a moment ago, ds is either equal to the square root of 1 plus f prime of x squared dx. That's the square root of 1 plus dy dx squared dx. Or if you're integrating with respect to y, it's the square root of 1 plus dx dy squared dy. We actually proved that. So, and in fact, that's what I write here. Proof, we just did it. Yay. Pretty nice. Again, the arc length function, this guy right here, doesn't creep in. Maybe out of every 10 problems, you get one that requires the arc length function. And I will have something like that, either in this lecture or in a video lecture. It just depends on how long this lecture takes. But that problem takes like 3 minutes, so it might be just within this lecture. And here's my warning. Because arc length always deals with, that's a weird sentence. Anyway, because arc length always deals with radicals, integration can be difficult or impossible. Numerical integration, unfortunately, is often used. So like I said, trapezoidal rule, Simpson's rule, midpoint rule, or method, however you want to call those. All right. So let's go ahead and just see a few examples. They go very quickly, so don't blink. I don't mean to rush through them. They're just kind of fast examples. There's just not much I can say about it. So this first one says, use Desmos to graph this. Now, obviously, if it were an exam, you wouldn't be able to use Desmos, but it's kind of nice to visualize. We're going to guess the length of the curve here. So I'll hop us over to Desmos. 2/3. All right, we're over in Desmos, and I'm going to type in here x raised to the 2/3 plus y raised to the 2/3 is equal to 1. You can actually graph implicit functions in Desmos like this, or implicit curves. And you can see this is actually very beautiful semi-diamond shaped, kind of a convex diamond shape, something like that. So we want to find the length of this curve. Okay. Now, here's the deal. the length of this curve, there's actually 4 sections to it. There's this first section, which I'm trying to click on, but it won't let me. So there's a section in quadrant 2, there's a section in quadrant 1, and then quadrant 4 and quadrant 3. They all look like they have the same lengths, and they actually do. So what I would do if I was to find the length of this curve is just to find one of the lengths, and maybe the quadrant 1 is the easiest, and then multiply that by 4. Now, we were asked to estimate the length of this curve. You could see that if we estimate, it'd be a very rough estimation. But if we want to estimate it, we could say, well, it's sort of like the length from the point 0, 1 to the point 1, 0. Let me write that in there. 0, 1 to 1, 0. So it's sort of like the length connecting those 2 points. That would be 1/4 of the total length. Of course, to be honest with you, that length is actually going to be shorter because a line is the shortest distance between 2 points. I'm sure you've heard that saying before. And if we have this bowed out little distance, that's going to be slightly larger than or longer than the line connecting the points 0, 1 and 1, 0. However, the length of the line connecting 0, 1 and 1, 0 is square root of 2. That's the length of that line. So we could say the approximate length of this curve is 4 times the square root of 2. That's what we could kind of ballpark it. So let me go ahead and hop back to my laptop. And write that in there. So this is just a kind of a rough estimate. For root 2, right? Because again, the length of that line connecting 0, 1 to 1, 0 is root 2. That's just a nice 45, 45, 90 triangle. So that's what our estimate is. And you know what? Let me get an approximation to that because I'm very curious how close we're going to get. 4 root 2 is 5.66. That's what we think the length is roughly going to be. It's actually going to be slightly larger than that, just because, again, the shortest distance between 2 points is a line, and we're actually going to develop a curve here. The curve is going to look something like that. So let's go ahead and find the length of that curve just in quadrant 1. I just want to know what is the length of that curve. So let me write that instruction down. There we go. Now to find the arc length, I happen to know, and I guess I'll use the lettering that the author uses. I use L for arc length. Actually, I'm still going to use L. There's a very specific reason. So I'm going to say the arc length, quadrant 1, by the way, so Q1, is going to be an integral from some number to some number of ds. That's it. That's the formula. There's not much else to it. And then we start saying, okay, well, do I want to slice with respect to x or with respect to y? I'm just going to let you know right now, it doesn't really matter which way you do it. It's the same formula. So if you take a look at our function right here, it's not even a function, but if you take a look at our relation right here, if you solve this for x or y, it's the same mechanics. And I personally like everything written in terms of x. I'm sure that you do as well. So let's just go ahead and do that. I think it's a much cleaner way of doing this. So I'm going to grab this guy, and I'm going to solve this for y. So I get y to the 2/3 is equal to 1 minus x to the 2/3. And that will imply, let me go ahead. Actually, I'll show you a clean way to do this. So I'm going to just clean this up right here. I'm going to say this is equal to the integral from x equals 0 to x equals 1. Now, remember, I started this course by telling you it'll be very important that you note in your limits what you're integrating, what variable you're integrating from and to. In other words, a lot of people write this, the integral from 0 to 1. However, noting what variable you're integrating with respect to is kind of important starting now, because you're going to have a lot of choices as we move forward. So you can easily convince yourself that you're integrating with respect to x when in reality you've chosen your limits as y values. So it's kind of nice. It's a little simple, extra little ink here, nothing huge, to say, okay, I'm going to integrate this from x equals 0 to x equals 1. And ds, I'll trade out for the square root of 1 plus dy dx squared dx. Now I look through that and I think, okay, do my limits match the variable that I'm integrating with respect to? And the answer is totally, yep, they sure do. So far I've locked into the correct variables. The next thing I'm going to do is find out what is y. Let me write it over here. And we already started solving that up above, but that's why I paused, because I wanted to get that formula written down so that I can showcase my mindset. Solving that formula for y, I get y is equal to the quantity 1 minus x to the 2/3 raised to the 3/2 power. I'll write that down. Y is equal to the quantity 1 minus x to the 2/3 raised to the 3/2 power. Double check my math there. Yeah. Okay, great. But I'm not integrating y, I'm integrating the derivative of y. So let's now ask ourselves, what is dy dx? You don't actually have to write these questions down. I'm just doing this so that you can see my thought process. So dy dx here, well, we have something raised to the 3/2, so that's going to be 3/2 times that something raised to the 1/2 times, by the chain rule, the derivative of the interior or the argument of that 3/2 power. And the derivative of that argument will be a negative 2/3 x to the negative 1/3. Let me do it this way. That way it's clean. So this looks pretty terrible, doesn't it? Your job is really to clean things up. So I'm going to clean this up. Notice that the 2's cancel beautifully and the 3's cancel beautifully. So that's kind of nice. So this will clean up to be a negative x to the negative 1/3 times 1 minus x to the positive 2/3 power raised to the 1/2 power. Still looks pretty terrible, doesn't it? I think so as well. So looking back at our integral, we see, well, we don't want just dy dx, but we want dy dx squared. So again, what is dy dx squared? So I'll just take that dy dx I just computed and square it. The square of this negative is positive. That's nice. Squares of things raised to powers, you multiply the power. So that'll be x to the negative 2/3 and then 1 minus x to the 2/3 power, because you're squaring the 1/2, which becomes 1/2 times 2. And now finally, what is 1 plus that? Some people don't do it in pieces like this, and that's fine. I don't judge you. It's just that if you don't do it in pieces like this, you're constantly rewriting that integration sign. And so and the square root symbol. And so this is just a nice way to avoid having to constantly rewrite that. I think. So 1 plus dy dx squared is going to equal 1 plus. And here I'm going to write it this way. I'm going to write it as 1 minus x to the 2/3 over x to the 2/3. because that's really what x and negative 2/3 times that picture is. And what you can do here is find a common denominator, which is x to the 2/3. And clean things up. And now let's plug that in our integral. Our integral is the integral x equals 0 to x equals 1 of the square root of that 1 plus dy dx squared, which we just computed to be x and negative 2/3. Remember, square roots are half powers, so that's going to be the integral from now I'm just going to write from 0 to 1, now that I have everything in terms of x. The integral from 0 to 1 of x and negative 1/3 dx. And this will be x to the 2/3 times 3/2 evaluated from 0 to 1, which is going to be 3/2. And now we're going to multiply that arc length that we found in quadrant 1 by 4. Now remember what our approximation was, 5.66, and I said that's going to be a little bit small because the shortest distance between 2 points is a line, and we don't have lines, we have curves, so our curve distance should be longer, and I said probably around 6, and it's exactly 6. So that is a really good clean. It's one of the rare clean examples you will get with arc lengths. It's clean because things canceled out when you took the when you were working with the radical. But that is a full arc length example. They all kind of run like that. And notice that I did it in little steps. I asked myself, what is y? Then I need to find its derivative and then square it and then add 1 to it. And then I worked with the integral. It's just cleaner that way. I personally feel you do not have to do it that way. If you want to do it all within integrals, step by step through that, more power to you. So questions on any of that? Arc lengths are pretty beautiful because once you get them, you really get them. Like there's very little that could go wrong with an arc length other than the integral being terrible. How did I factor x to 2/3? Do you mean how did I take the square root? Or I'm not 100% sure what you mean by how did I factor. For 1 plus d, oh, so this piece right here. So are you okay with this 1 plus dy dx squared being 1 plus the 1 minus x to 2/3 over x to 2/3? Does that make sense? Okay, perfect. Then it must be this step right here, I'm guessing. So 1 is the same thing as x to 2/3 over x to 2/3, right? And so now that they have this 1 and this fraction have the same denominator, I glued them together. And notice x to 2/3 minus x to 2/3, they cancel. So you have 1 over. And that ends up 1 over something is just x to the negative power. Yeah. All right. Let's do another example. Yeah, no problem. Determine the length of this curve. Now, this problem can be done 2 different ways. And we can go ahead and do it both ways. So determine the length of this curve on this terrible looking interval. Look at that interval. It goes from 0 to 2/3, 3 to the 3/2. There's a very specific reason why it goes to that terrible number. It's because it's clean if you do that. But somebody says determine the length of a curve. I immediately think, oh, the length of a curve is just the integral from a to b ds. That's it. I need to make 2 choices, really 1 choice. Do I want to integrate with respect to x or with respect to y? Since they gave me the function y equals f of x, I'll integrate with respect to x, at least for right now. So I'm going to trade this out for an integral from x equals something to x equals something of the square root of 1 plus dy dx being squared dx. Now, you don't have to do it with respect to x, actually. This problem works both ways. And in fact, it's easier to do with respect to y, I think. I'm not sure. I can't remember. But for right now, let's go ahead and just pretend as though we're doing this with respect to x. Not pretend, we're actually doing this with respect to x. So if I did this with respect to x, first of all, x would go from 0 to that terrible 2/3, 3 to the 3/2 power. Off to the side, I'm going to go ahead and in blue, maybe, excuse me, just find out what the derivative is, square it, and add 1. So the derivative with respect to y of x is going to be 2/3 times 3x over 2 to the negative 1/3 power times, by the chain rule, 3/2. And beautifully, these 2's cancel, these 3's cancel. Don't get used to that. That's not always going to happen, but at least we get there. And now I could say, oh, therefore, dy dx squared is equal to that 3x over 2 to the negative 2/3 power, because you're just multiplying the exponent by 2 when you're squaring. And that will imply 1 plus dy dx squared is just 1 plus that. Now, I'd like to get this down into a single term. When you take the square root of something, it's much easier to take the square root of a single term because you could break things apart and take square roots of pieces rather than the square root of a sum or a difference. If I leave it as a square root of a sum, I can't break the square root apart. That ends up being really, really challenging. So instead, I'm going to go ahead and try to get this glued together as the same problem. To do that, I'm going to write it this way. This is 1 plus 2 over 3x to the positive 2/3 power. So all I did was take the reciprocal and get rid of the negative exponent. And now, honestly, I think that this is just going to be a terrible, terrible problem. Maybe, is there a better way to go about that? Well, not really. 1 plus 2 to the 2/3 over quantity 3x to the 2/3. Get a common denominator. And you get to that point right there, and there's really not much you can do that you think. You actually can do this. Let's go ahead and plug that in. That is actually 1 plus. So let's go ahead and plug that in. You get the integral from, now everything's going to be in terms of x, so I don't need to write x equals. And we have the square root of this simplified, even though it looks pretty ugly, that simplified fraction, which is 3x to the 2/3 plus 2 to the 2/3 over 3x to the 2/3. And then we have a dx. As I mentioned at the beginning of this section today, your integrals will look really terrible when you're dealing with this. That's just, there's no way around it when you're dealing with arc lengths. The integrals get really ugly. However, I I can at least take the square root of that denominator and pull it out. I would get 1 over 3x to the 1/3. That's the square root of that denominator. In the or in the radical there, I'm going to write it this way. I'm going to write 3 to the 2/3, x to the 2/3, plus 2 to the 2/3 dx. Not much you can do there. However, this actually is workable. Believe it or not, this is not impossible. I will at least take that 3 to the 1/3 and I'll move that out front. And we're left with x to the negative 1/3. Or 1 over x to the 1/3, but trust me, it's easier to see this if you write as x to the negative 1/3. Now, at this point, a u sub will actually solve this problem. Excuse me. If you do a u substitution here, du will steal away a 2/3, 3 to the 2/3, x to the negative 1/3 dx. Now, let me simplify that to showcase exactly what it will steal away, because it's not so obvious. Times, that's a times. And if you don't see it, oh, there's a dx too. If you don't see it, we have a lot of that to steal away. A dx, it's right here. X to the negative 1/3, right there. 3 to the negative 1/3 is actually what that is. So this actually simplifies fairly quickly. The 2 I'll have to bring over, so it's going to be a 1/2 integral from u equals something to u equals something of the square root of u, or in other words, u to the 1/2 du. So it does compress down really, really quickly. Now, when x is 0, because I need to figure out what my limits of my integral are. When x is 0, u is 2 to the 2/3. Excuse me. And when x is this nasty upper business, now I'll have to actually figure that out. Let x equal 2/3, 3 to the 3/2. That implies u is equal to, well, here's u right here. I'm plugging it in. We have 3 to the 2/3 power times x to the 2/3 power plus 2 to the 2/3 power. X is 2/3 times 3 to the 3/2. You can break that apart. It's a little bit of mechanical work, but you can see beautifully. Remember, powers to powers multiply, so these 2's will cancel, those 3's will cancel. You get a 3 there. You have a 3 to the 2/3 here, but it's multiplying by, or basically dividing by 3 to the 2/3 there. So those 2 cancel. So you get the following: 2 to the 2/3 times 3 plus 2 to the 2/3, or in other words, 4 of those 2 to the 2/3 power. A lot of little mechanics in there. It's algebra. So I'll leave it to you. Doing the integral, you're going to go ahead and add 1 to the exponent and multiply by the reciprocal of that. And we're evaluating this, excuse me, from 2 to the 2/3 all the way until 4 times 2 to the 2/3. This will equal 1/3 times, we have 4 times 2 to the 2/3 raised to the 3/2 minus 2 to the 2/3 raised to the 3/2. Cleaning this up, we'll get 4 to the 3/2, actually is doable, times 2 to the 1st minus 2 to the 1st. 4 to the 3/2 actually is the square root of 4, which is 2 to, raised to the 3rd power. That's 8. 8 times 2 is 16. Minus 2 is 14. This is 14/3. As I mentioned again, just to remind you, at the beginning of the section, the integrals can be a bit gnarly. A lot of little algebra in there. How did the second term get canceled? I'm finding the second U. I'm sorry. I'm not 100% sure. You mean in this area right here? Okay. How the second term get canceled? That's the second term. Oh, no, it didn't get canceled. I see. It didn't get canceled. If you take a look at this, I have 1 of those right there, and I have 3 more of them right there. 1 plus 3. I have 4 of them all together. That makes sense? Yeah. Now, let me just tell you that this is an enticing problem to go the wrong way. What I mean by that is it's very, very, it's written to make you not think, because it's written already solved for y. Y is equal to a function of x here, and they give you the interval x going from 0 to 2/3, 3 to 3/2. However, if you took the time at the beginning to say, I wonder if I could do this in terms of x, and forgive my use of red for this, it's just I used all my other colors in this problem. Did I use green? I sort of used green. So let me use red for this. If you had started the problem and said, you know what, I'm going to find this arc length with respect to y. Well, you could totally do that. You get y minus 1 is equal to 3x over 2 to 2/3 power. Raise both sides to 3/2. Multiply by 2 and divide by 3. So that would be our function x in terms of y. Of course, if you were to want to do this problem this way, you have to change your limits. Your limits can't go from x equals 0 to x equals something else. Instead, you'd have to go from y equals something to something else. So x being 0 implies that y is equal to going over to this piece right here. If x were 0, y is just 1. X being 2/3 times 3 to the 3/2 implies y is equal to 3/2 times that x to the 2/3. Wait, is that 3/2 on the inside? Yes, it is. 3/2 times that x to the 2/3. And then I think it was a plus 1. Yeah, plus 1. If you take a look at that, Threes cancel, twos cancel, threes cancel, twos cancel. That is going to be a 3 plus 1 or 4. Again, if you had taken the time, you being proverbial you, not you, but just us in general, if we had taken our time at the beginning and said, I wonder if doing this in terms of y would be easier, the answer to that question is, yeah, it would be. Because then you'd have the arc length equaling some integral where you're adding up a bunch of arcs. And if you do it in terms of y, you're going from y equals, well, if I look up above, when x was 0, y was 1. When x was that other mess, y was 4. So it's integral from 1 to 4 of the square root of dx dy squared plus 1. Doesn't actually matter which order you write that in. Dy. Now, up above, I'm going to go ahead and find out what's dx dy squared. I know what dx dy is. Dx dy is bring down the 3/2 power. It'll cancel with 2/3, and you get y minus 1 to the 1/2. Thus, dx dy squared is y minus 1. Add 1, and it is just y. This would be the integral from 1 to 4 of y to the 1/2 dy. Antiderivative, y to the 3/2 times 2/3 from 1 to 4. 2/3 times square root of 4 is 2. Cubed is 8 minus 1. That's 7, 14/3. That is a very poignant example, impactful example, because it showcases if you take the time at the beginning to determine what variable would I like to integrate with respect to, when you start dealing with arc lengths, you have choice. So don't be enticed totally by how they hand you something. Take a moment and ask yourself, would it be better to do this with respect to y? As you can see, that is a ton easier when we did it with respect to y. A lot easier. So that's just a heads up. Very, very, very powerful example. The last example is an online example, so I'm going to leave it as an online example so that we can get into the second section we're going into. And don't think that it's like, oh my gosh, we're rushing through. These are actually very short sections. So that very first section, it was all about that one formula. That's it, arc length.